All right. Whoops. We've already did all that. To example 4 is where we left off. Okay. So here's the second part of our video. All right. So next example for 4 here, we're going to test the summation from n equals 1 to infinity of n squared times e to the negative n cubed. So let's move this to the bottom and take its limit. And I see that this is infinity over infinity. So we're going to have to do L'Hopital's rule to keep breaking down the top and the bottom. So that's 2x over e to the x cubed. Then the derivative of x cubed is 3x squared. Well, still infinity over infinity. You can take L'Hopital's rule again, and you get 2 over. Now you got to use the product rule here. So that's going to be 3x squared times the derivative of this, which is what we have in the denominator. So 3x squared times 3x squared is 9x to the fourth, times e to the x to the third power, plus the derivative of the first function, 6x times e raised to the x cubed power. Well, the bottom's getting bigger, the top staying constant, so that's 0. Now, don't get me wrong, we could have stopped right here. You could have canceled this x with the x and x squared, and you would have had 2 over something getting bigger and bigger and bigger, which is 0. So check your simplifying before continuing on with all those L'Hopital rules. So let's check to see if we can do the integral test. Change it to a function. It is continuous. It is going to be positive. And yes, we're decreasing because, again, obviously here, x cubed gets bigger faster than x squared. And then that x cubed is an exponent on base e, which makes this get even bigger faster. So yes, it's decreasing. All right, so we write our improper integral. We put in our limit notation. T goes to infinity. And let's integrate this. So let's see. I see x to the third. I see x squared. I see a u sub happening here. So let's let u be negative x cubed. Then du will be negative 3x squared dx. So we're just going to have to divide over that negative 3 once we plug it in. Also, while we're here, let's change our boundary so we don't have to back substitute this in. So your upper bound is t. I plug that in over here for x. That's negative t cubed. That's going to be our upper bound for u. Take the 1, plug that in over here for x. That's going to be negative 1. So rewriting this will be negative 1/3. There's the negative 3 we had to divide over. The limit as t goes to infinity for our integral now from negative 1 to negative t cubed of e to the u, which is great to integrate because that's just the same thing, e to the u. Let's evaluate it with our bounds. So negative 1/3 times the limit as t approaches infinity of e to the negative t over 3 minus e to the negative 1. Okay, wait a minute. That's going to move e to the t cubed power into the denominator, so 1 over that, so that's going to approach 0. And minus 1 over e, if you will, or you can still leave it as negative e. But either way, when we multiply that out, a negative times a negative will be a positive, 3 times the e on the bottom, 1 over 3e. So this integral converges. And again, therefore, so must your summation of your sequence function also has to converge. Now again, remember, this is not the sum for the summation. All right, it's just a confirmation that we are converging. All right, next examples we're going to look at are summation of sums. And we have a very special one coming up here where n is in the denominator raised to a positive p-value, some positive constant. If we have that, that's called the p-series. All right, and we have a special p-series is when p is equal to 1. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. That is called a harmonic series. Again, p-series are not geometric. All right, so definition, the p-series, the summation of 1 over n to the p will converge if p is greater than 1 and diverge if p is less than or equal to, wait a minute, I've seen something like that before. Yeah, that was back in section 7.8 when we were doing our improper integrals and proved that when 1 to infinity of 1 over x to the p power would converge if p was always greater than 1, and it diverged if p was less than or equal to 1. All right, so again, there is that theorem that says, okay, if it works for functions, then it's going to work for summations when we do infinite sums. All right, example time. Let's look at this series here, see if it converges or diverges. So 1 plus 1 over 2 times the square root of 2 plus 1 over 3. Wait a minute, I see a pattern here. This 1 is 1 over 1 times the square root of 1. Then that's when n equals 1, n equals 2, n equals 3, 4, 5. So this is 1 over n times the square root of n. And that's going to be a summation up to infinity. So let's simplify the bottom. That's n to the first times n to the 1/2, which is n to the 3/2 power. I don't have to go any further. I'm going to my rule. P is 3/2, and it's greater than 1. This is a p series, and that converges. Now, we don't know what the sum is. We just know that it converges. Again, geometric series, we can actually find that sum. Telescoping, we can actually find that sum. P series, we can't. All right. Continuing onward, B. Oh, I'm done. N to the 7th power. This converges. My P is 7. It's greater than 1. It converges. You're going to love the P series. It makes things really quick. Let's see. This is going to be a P series 2 because I have n to powers here. But I need to make just one n. So let's see. Divide like basis. 2 minus 5/2 is a negative 1/2 on my n. So that's going to stay in the bottom. So 1 over n to the 1/2 power. Okay, p is 1/2, but that's less than 1, so this diverges. Remember, greater than 1 converges, less than or equal to 1 diverges. D is, wait a minute, this is not a p series. We don't have n raised to a power, so this has n in the exponent. That's going to be geometric. So that puts this on the bottom. Let's take the 5 out to the front. 1 over e to the n is... We can change that for our base to be 1 over e, all raised to the nth power. So that makes this geometric, not a p series. And because it's geometric, we can actually find out where it converges to. So our r is 1 over e, which is less than 1. So we can use that infinite sum formula, a sub 1 over 1 minus r. So we got to find that first term. So I had to plug the 1 back in to n, so that's 5 over e, that's a sub 1. All right, 1 and over 1 minus r, the 1 over e. Let's see, to simplify this, multiplying e top and bottom, cancel, cancel, and e times 1 is e. So this is a converging series, which just happens to have the sum as 5 over e to the e minus 1. All right, example 6. Let's see, let's try this summation. See if it's going to converge or diverge. The divergent test, I think this is going to have a limit of 0 because we can see that the top has no ends there. The bottom's getting bigger, so the limit's 0, so it doesn't diverge. Is it continuous? Yes, no vertical asymptotes. Because this is a 0, there's no conclusion, so we got to keep working on it. So it's continuous. Is it positive? Yes, because all your x's are going to be 1 or greater. Is it decreasing? Yes, the bottom's constantly getting bigger. The top stays the same, so that's decreasing. We can see that. All right, so we write our improper integral. We change it to our limit notation. And man, this looks familiar. Oh yeah, wait a minute. Factor out the 7. I see a u squared plus an a squared on the bottom with 1 on the top. That's one of my special rules. That's our integral table rule for inverse tangent here. So 1 over u squared plus a squared du equals 1 over a times the inverse tangent of u over a. So x is my u, 5 is my a, so let's substitute it in. So 7 times the limit as t goes to infinity of 1/5 times the inverse tangent of x over 5. We'll evaluate it from t down to 1. So plug in the t, plug in the 1. So what I did is this 1/5, we don't want that in here when we evaluate it, that's just excess writing. So I factored it out to the 7, called it 7/5. Okay, inverse tangent graph, I got to remember what happens here. So we look up our inverse tangent graph. We have horizontal asymptotes at pi over 2 and negative pi over 2. So as my t takes me to infinity, my x's are getting incredibly huge here. So we're approaching pi over 2 as we head out to positive infinity. So that's where this is approaching to, minus the inverse tangent of 1/5. That's a constant. So our answer is 7/5 times pi over 2 minus the inverse tangent of 1/5. So this is something other than 0. The integral converges, and therefore so must the summation also converge. But again, this is not the answer to the summation. This just confirms that we are converging. Okay? All right. So, next set of examples here. Let's look at your tests and your series that we can use. So the only two tests that we have so far is the divergence test and the integral test. Our series are geometric, telescoping. Again, remember, these two can actually find the sum. And your p-series, this one you can't find the sum, so make a note. All right, so again, for p-series, you have to have n raised to a power. Geometric, you have to have, let's see, your n has to be in your exponent. And telescoping, you have to have fractions being subtracted, or there's negatives in there, which causes us to run into the problem of not having positive function. So let's see. Looking at this one right here, well, I see n squared on the top, n cubed on the bottom, top smaller than the bottom. So this will have to be an integral test because remember the limit would equal 0, so the divergent test isn't going to work. So we are positive everywhere, squaring and cubing positive numbers, adding positive numbers. It's continuous and it's decreasing because the bottom's getting bigger faster than the top. This, we got a -1 in here. That's a bad sight right away because we can't do the integral test because it's not positive. So that tells me, I think we're going to have to do a telescoping series. We would actually have to take this and factor the bottom and do a partial fraction decomposition. It is a proper fraction. All right, top is smaller than the bottom. This is technically n to the 0, n squared, so it's a proper fraction. Okay, number 3, let's see. Well, we're going to have a p-series here because we have n raised to positive powers. So you would want to go 1 minus 7/2, so that's n to the 5/2, so that 5/2 is greater than 1, that would converge. Here, now my n is in the exponent position, so that's going to be geometric series. And here on the bottom, wait a minute. We got a problem. No, we don't. We actually have a great problem. The top power is bigger than the bottom power, so the limit of this has to be infinity, which means your divergent test says that your limit doesn't exist and it doesn't equal 0. So that's going to diverge. And we're done. So get used to how to recognize what test to use and what series to use. Why does my mouse keep sending me backwards? This is worse than my clicker in class. All right, so that wraps up that second part of section 11.3. All right, let's see if I can not mess this up.